Our next speaker is Professor Michael Hopkins. I had the very good fortune of meeting Michael when we both were graduate students in Oxford. And I must say that since those days, one could clearly see that he was absolutely outstanding. In fact, while we were all struggling to survive in our graduate studies, Michael was doing simultaneously two PhD at the same time. One in Oxford, where I was, and at the same time at Northwestern. And in the two places, he was working with the top algebraic topologists of the time, doing very, very, very good work. He got both of his degrees, if I'm not mistaken, in 1984. Then he has been professor of mathematics at Harvard since 2005, after spending 15 years at MIT and a few years at Princeton. He gave an invited address at the International Congress of Mathematicians in Zurich in 1994, and he was a plenary speaker at the 2002 International Congress of Mathematicians. He has been awarded several prizes, and but I think I can say that perhaps, this is my interpretation, perhaps his greatest award, I don't know, or a very large award, is having proved recently in joint work with Douglas Ravenel and Michael Hill, a long-standing problem in algebraic topology, a problem in which almost every algebraic topologist had a thought and had a priori a frustration, which was known the Kerver or Arf-Kerver invariant. That long-standing, very deep, very interesting problem started with arose with a work by Kerver, and then in later work by classical work by Kerver and Milnor about groups of homotopy spheres. It was that invariant, that problem played a very, very crucial role. That was published in 1963, and since then it was open until a few years ago. We can say that Hopkins' work has indeed revolutionized the field of algebraic topology. He has pioneered applications of homotopy theory to a range of areas in mathematics, collaborating with geometers, number theorists, and mathematical physicists. It is a privilege to have Professor Hopkins with us today. Please join me in welcoming him.
Well, thank you, Pepe, for that wonderful introduction. It's an honor to be here and get to help celebrate the 75th anniversary of this center. For me, I've made many trips to Mexico and have many friends here, but this is the first time I've been here when my friend Sam Gittler wasn't. So Sam was a very important person in algebraic topology and in my life, and you'll see some of his work explicitly and implicitly in the things I want to talk about. So this is a joint project with Aravind, Asok, and John Fasel, and it has to do with applying methods of homotopy theory to solve a problem in algebra. And I was really struck during Maury's talk when he was talking about how these problems in algebraic geometry over the complex numbers, you can, if you're approaching it algebraically, you have available reducing mod p, finding integral models that you can reduce mod p and letting Frobenius act. And if you're thinking about complex analytic methods, you have semi-analytic sets, and that these two really belong to their own domains and yet get brought to bear on the same problems. And in a way, my main theme is something very analogous. That there's a problem, this problem of classifying algebraic vector bundles that one can approach with complex analysis with algebraic geometry, and now also with the methods of homotopy theory, and they give really different looks on the same problem. So just to recapitulate this a little bit, one of the things when you learn about the development of algebraic topology and homotopy theory is that the subject kind of develops as more and more problems in geometry and other parts of mathematics become seen as problems in homotopy theory. And these things, even though they have origins outside of the subject, they wind up getting solved within homotopy theory, and it has its own peculiar little tools and constructions that you don't really see outside of the subject. I mean, think of these things as analogous to reducing mod P and letting Frobenius act. One of them is homotopy groups, maps from a sphere to a space up to deformations. Those are very important. They've appeared in several talks here. David Gabay mentioned homotopy groups in his talks. And yet one only really knows how to work with them using kind of methods in homotopy theory. And homotopy groups are used in homotopy theory to manufacture spaces out of cells. And again, that's something peculiar to the subject. This notion that a space is decomposed into cells and that you understand a space by homotopy groups and attaching cells is also something very much in homotopy theory. So here's a picture of a manifold, a torus, decomposed into cells in a way that in this case isn't particularly geometric. But there's many, many more things in homotopy theory like this. There are spaces like Eilenberg-MacLane spaces, which have a unique homotopy group. There's Postnikov towers, spectra, Steenrod algebra, there's Brown-Gittler spectra, there's Sam's name again. And these are all objects that are used within homotopy theory that are very hard to see outside the subject, that are used and brought to bear on these problems that are discovered to be homotopy invariants. So as I said, up until about the 1970s, there tended to be problems in geometry, sometimes algebra, that were seen to be homotopy invariant or seen to be problems of homotopy theory, meaning they were invariant of deformations. And in the 1970s, there were many, many models for doing homotopy theory, and Quillen and Dan Kahn and others introduced what we now call abstract homotopy theory, which gave a way of attempting to use the methods of homotopy theory in really different categories. And, but that was in the 1970s, and that didn't really take off outside of the subject until around 2000. And today, many mathematical questions are seen as questions in homotopy theory, and often they're approached using abstract homotopy theory. So that's what I want to talk about today. And the question I want to talk about is which complex vector bundles on a space have algebraic structures? So on a complex algebraic variety. So this is a problem, I mean, this is far from being solved, and it's a problem it's a very difficult problem, and it's quite an interesting problem. So it was investigated intensely in the 70s, both by algebraic geometers and by analysts. Griffiths studied this problem in connection with the Hodge conjecture. If you could show, so you know every rational cohomology class is a Chern class of a vector bundle. If you knew that vector bundle had an algebraic structure, then you would have lifted that to an algebraic cohomology class, and you'd solve the Hodge conjecture. So Griffiths was very much interested in this problem, and the methods Griffiths used were really located in complex analysis. So it suffices to consider this over smooth affine varieties, and by a theorem of Grauer, such vector bundles have a unique holomorphic connection. And Griffiths tried to measure the obstructions to that having an algebraic structure in terms of the growth rate of the connection. So his obstruction was expressed in terms of Nevenlina theory or value distribution theory, and he gave some obstructions in terms of the growth rate of a connection. And so I'm going to talk about some obstructions that come from a very different source and are in principle comparable to the Griffiths obstructions, but we don't know how to compare them yet. This question was also investigated in algebraic geometry by many people in connection with, well, the zero section of a line bundle is a codimension 1 subvariety by an analogous theorem of Serre and Hartshorne. In good cases, codimension 2 subvarieties are all gotten by zero sections of rank 2 vector bundles, and classifying vector bundles tells you a lot about the internal geometry of the variety. So there were many, many people interested in this question of classifying, or the existence and classification of vector bundles in algebraic geometry. But where I really want to start is with the conjecture of Serre's, or an observation of Serre, because this is where it looks like the question of classification of algebraic vector bundles could, in the first place, be a problem in homotopy theory. So in Serre's famous 1955 paper on algebraic coherent sheaves, he identifies this correspondence between vector bundles on a variety or a space and finitely generated projective modules over the ring of functions. And in Serre's case, X was an algebraic variety, or an affine algebraic variety even, and so that's just a ring, a nice ring, but X could be a topological space, that could be the ring of continuous functions, or it could be something much more elaborate. And he made this remark in that paper that when X is affine R space, he didn't know if there were finitely generated projective modules which were not free. And so that corresponds to a theorem in topology that vector bundles are homotopy invariant. A vector bundle over a space cross an interval is always pulled back from a vector bundle over one of the ends. And in particular, a vector bundle over affine n space has to be trivial. And Serre just made this remark that he was clearly thinking about the analogy with algebraic topology, and he just made this remark that he didn't know if there were non-trivial vector bundles in algebraic geometry. Well, so this was a remark which of course soon became known as Serre's conjecture, even though he didn't state it as a conjecture or a problem. And it was solved also in the 1970s almost simultaneously by Quillen and Suslin. And they showed that if you're over a field, then indeed every finitely generated projective module is free. So with this work, it began to look a lot like ordinary geometry. Algebraic geometry started to look like differential, or even just look like topology, that vector bundles over contractible spaces had to be trivial. And so the next step was taken by Bass and Quillen, and they built on this idea that vector bundles over a space cross an interval are the same up to isomorphism as vector bundles over a space. This fundamental thing that bundles are homotopy invariant meant that bundle theory, the study of bundle theory, could be located in homotopy theory, and that's one of the big sources of problems in geometry finding themselves located in algebraic topology. So they made the following question. They made the following conjecture that if X is well, in their case, a smooth algebraic variety, are algebraic vector bundles up to isomorphism homotopy invariant. So you replace the space X by a smooth variety, and you replace the affine line, the unit interval, by an affine line. Now, I'll give you some examples of this in a minute, but I want to say there is a lot of question about for which X one expects this to be true, and it's not true for projective varieties. You need to assume X is affine, but I'll get into some simple examples of this in a minute. So they phrase this entirely in terms of algebra, and for the purposes of this talk, you don't really need to parse what I've written here, but I just wrote the analogous statement so I could say something precise. But this basically says that a vector bundle over something cross a line is pulled back along the projection map from a vector bundle over the thing you started with. And the Bauss-Quillen conjecture was proved by Lindell, building on Quillen and Susslin's methods in 1981, at least in the case when the ring A was a regular ring over a field. So it was the affine coordinate ring of a smooth variety over a field. And this, well, I think it's, this is a wonderful story, and I recommend, if you want to learn more about it, T.Y. Lamb's book called Sayre's Problem on Projective Modules. So the situation was really well summarized by Frank Adams in a math review he wrote of a couple papers, which I've listed below, and he basically said, I've kind of been stealing from him when I started this talk, that he basically said, you know, well, you can read it up there, but there seemed to be a kind of program where one takes some idea from bundle theory, expresses it in terms of projective modules, and then tries to prove the analogous thing in algebra. And this had, this was, I mean, these results tended to be true, and it made one think that bundle theory really could be studied using homotopy theory in algebraic geometry, just like it is in the algebraic topology of spaces. So we arrive at this question, can algebraic vector bundles be studied using homotopy theory? Now, this homotopy theory can't be the usual homotopy theory of spaces. We don't have a unit interval in algebraic geometry. We could try to imitate some of the methods, but it's a good idea to just take advantage of the existing groundwork and think of this first. First, just let abstract homotopy theory get us organized in thinking about the problem. So I want to take a few minutes and just say what abstract homotopy theory is. So this took many years to arrive at this definition. As I said, it was introduced in the 1970s, but it wasn't until almost the 2000s that the definition and the point of view is boiled down to what I'm about to tell you. So you're doing abstract homotopy theory whenever you have some category and some class of maps that you want to regard as equivalences. So for instance, we might be looking at algebraic varieties, and we might want maps of the form x cross an affine line to x to be equivalences. And so, or we want to study things that don't see the difference between x and x cross an affine line. So the abstract setup is you have a category and a collection of maps that you want to regard as equivalences, and for traditional reasons, these maps are called weak equivalences. And what you're interested in studying are invariants of your objects or functors to another category that don't see the difference between weakly equivalent things, functors that take weak equivalences to isomorphisms. So for instance, by Lindell's theorem, well, I'll get to that in a minute. So, all right, so the other feature, so that's the basic setup, and the other feature of abstract homotopy theory is that there's a universal homotopy invariant functor, a functor from your category to something called the homotopy category, which is universal for functors that don't see the difference between weak equivalents, that don't see the difference between weakly equivalent objects. And so this is the general abstract setup. You're studying some category, some weak equivalences, and you're trying to understand the structure of the homotopy category. And what you do in all of these situations is you disassemble the objects in terms of simpler objects, which might not have been the kind of objects you would have considered before, and you can apply the methods of homotopy theory to understand things. Anyway, I'll get to some examples of that in a minute. Let me give you some examples of abstract homotopy theory. So the prototype, the first one, is ordinary homotopy theory, where you have the category of topological spaces, and W is the class of homotopy equivalences, or maybe weak homotopy equivalences, which are maps that are isomorphisms of homotopy groups. So that will come up, and I will indicate that with a top as a superscript, and that's just classical homotopy theory. And in that case, the homotopy category is the usual homotopy category. And rather than write this for the set of maps in the homotopy category, I'll use this symbol with square brackets. Okay, so there's another one that's of use in algebraic geometry. So let's suppose we want to study invariants of varieties. That means to every variety I have maybe a set of objects, and to every map I have a map of sets, or maybe these are simplicial sets, some combinatorial object that's recording a bunch of invariants and the relationships between them. So formally, though this isn't necessary, if you don't know these words, it's not necessary for understanding the talk, we're looking at simplicial presheaves on smooth varieties. And so those invariants at that level of generality don't capture one important property of algebraic geometry, which is that you want to, well, here's a picture. You want to, when you have something written as a union of two pieces, you want to say that the invariants you're studying over the whole space X can be gotten from studying these invariants on the intersections subject to some, on the open sets, subject to some kind of compatibility on the intersections. And you can express that in this abstract homotopy relation. You want to say that the diagram that expresses a space as a union of open sets glued along intersections is a weak equivalence. And so you can introduce that, and you get an abstract homotopy theory, which I'm just going to call algebraic homotopy theory. So this was introduced in 1973 by Ken Brown and his thesis, and it's very useful for getting organized, but you can think of all the cohomology theories you can think of as representable by Eilenberg-MacLane spaces. You can import a lot of structure from algebraic topology into algebraic geometry, but it's kind of a formal point of view, and it often doesn't really, well, I'll show you an example in a little bit. It doesn't really reveal structure that you weren't seeing from the point of view of classical algebraic geometry before that. But nevertheless, there is this algebraic homotopy theory where we can kind of locate a lot of classical algebraic geometry. And in particular, though, well, so then around 2001, Morel and Voevodsky introduced motivic homotopy theory. So in motivic homotopy theory, you take the same collection of things we were looking at in algebraic homotopy theory, but you force the affine line to be contractible. Okay, so in motivic homotopy theory, you're looking at varieties. You're saying that a variety is the union of its open sets glued along intersections, and I'm saying the affine line is contractible. And I can formulate that, I can articulate that in this context of abstract homotopy theory with these kind of weak equivalences. All right, and in that case, that's called motivic homotopy theory, and it had some spectacular applications in the study of algebraic K-theory. Voevodsky used it to prove the Milnor conjectures on quadratic forms, and Morel's made spectacular applications to other invariants. So this is motivic homotopy theory. So just if that seemed abstract, that's the end of that abstract part. But when the day is done, we have three kinds of places we can do homotopy theory. There's the homotopy theory of topological spaces. On the right, there's motivic homotopy theory, and then there's purely algebraic homotopy theory. Okay. So there's a relations between them, which I'll just call realization functors. If I have an algebraic variety over the complex numbers, I can regard it up to motivic homotopy equivalences, and I can regard it as, I can look at its underlying analytic space and locate that in ordinary algebraic topology. Okay, so I said what we really want to do is bundle theory as expressed by atoms and as foreshadowed by Serre and Bass and Quillen, and we want to study bundle theory from this point of view of homotopy theory. So bundles are classified by maps into a classifying space. The first example we all learn about is Milner's construction, and this was modified a little bit after that by Graham Siegel, who gave a simplicial classifying space. So this is something, if G is an algebraic group, this is an object that makes sense as a simplicial presheaf. So in my sequence of categories, this object makes sense all the way back in algebraic homotopy theory. So in ordinary topology, when I take this is the classical theorem that the set of principled G bundles is the set of homotopy classes of maps into this classifying space. And if G is the general linear group of the K by K general linear group of the complex numbers, or the unitary group, then this is the set of K-dimensional vector bundles over X up to isomorphism. So it's also true back in algebraic homotopy theory that vector bundles up to isomorphism is given by homotopy classes of maps into this same classifying space. But this is not a very deep result. This is just a reformulation. If you unpack all the definitions, this is just reformulating the local description of vector bundles in terms of charts and transition functions. So we have a way of expressing algebraic vector bundles and topological vector bundles in terms of homotopy classes of maps, or in terms of maps in two different homotopy categories. And this makes it seem natural to look at the same set of maps in the motivic homotopy category. So right now we don't know any relation between anything about this. I'll call these motivic vector bundles, and the realization maps give me a map from the set of algebraic vector bundles to the set of motivic vector bundles, and then there's a forgetful map to topological vector bundles. So if I was interested in the problem that I mentioned before of taking a vector bundle, a complex vector bundle I might produce in algebraic topology and finding an algebraic structure on it, that problem would this breaks it into two. First, I might try to find a motivic vector bundle, and then I might try to give that motivic vector bundle an algebraic structure. Okay, so the first thing I want to point out is those different kinds of vector bundles aren't that different. So there's a fantastic theorem originally due to Morel, and it was given a much simpler proof by Asok, Oiwa, and Wendt just a couple years ago. And that says that if you have a smooth affine variety, there's no difference between algebraic and motivic vector bundles. So you can think of this as really the ultimate expression of what Serre was hinting at in his question about the homotopy invariance of vector bundles. This says it exactly happens in algebraic geometry the way it happens in algebraic topology, that algebraic vector bundles is homotopy classes of maps into a classifying space, where by homotopy we really mean algebraic homotopy. So this is this paper of Asok, Oiwa, and Wendt is really great. It's almost a place you could start learning motivic homotopy theory from, and it's a really, I highly recommend that paper if you're interested in this subject. Anyway, this I think of as really the ultimate expression of this, at least over fields, of this theorem, of of this arc that kind of began with this observation of Serre. So that's true for affine varieties. What happens with projective varieties? Well, I've written down an example here, but and I'll put it up in case you want to look at it, but maybe I'll just say what this is. This is an example of a one-parameter algebraic family of vector bundles on the projective line, where the vector bundle at 0 and the vector bundle at 1 are not isomorphic. And if you want, it's just the extensions of O of 1 by O of minus 1 form a vector space, and I can draw a path from a non-trivial extension to the split extension, and those vector bundles wind up being non-isomorphic. So this simple example is just there to point out that you can't even expect vector bundles over projective varieties aren't homotopy invariant in the first place, and it's not so clear how one might even locate them in motivic homotopy theory. Okay, so one naive question, I believe the answer to this is no, but I don't know for sure, that one might express sort of the moduli space of motivic vector bundles on X in terms of algebraic vector bundles up to homotopy. It might be that the most naive thing happens, that you just take the quotient of all vector bundles by the equivalence relation of homotopy, and you get motivic vector bundles. So this is probably wrong, but I don't know. It's correct for P1. It's correct for P1. If you knew it for projective spaces in higher dimension and for k equals 2, by some results I'm about to describe later, you'd have counterexamples to some famous conjectures. So I don't know what's going on, what the relationship here is, but I think it's a really interesting question. So there is nevertheless something you can do. You can locate this construction of motivic vector bundles on projective varieties entirely in terms of algebraic geometry. And that's due to this really cool trick due to Joannolu called Joannolu's device. So I think the coolest thing, the easiest way to explain it is to just take an example of something that's not an affine variety, which is you take the affine n space and remove the origin. So if n is greater than 1, that takes more than one equation to define, and so the complement to the origin won't be an affine variety. Any function that vanishes, it won't be an affine variety. Okay, but you can make it an affine variety by giving the vectors x1 up to xn a reason for not being the 0 vector. So instead of looking at vectors x, look at pairs of vectors x, y, so that x dot y equals 1. Now, the difference between any two y is a vector such that x dot y is equal to 0, and the solutions to that is a vector space. So this space of pairs like that maps to the affine n space minus the origin, and the fibers are affine spaces. The difference between any two of those is a point in a vector space. So that's an equivalence in this motivic world. And so what I've done is shown you that I can find, even for this non-affine variety, the affine n space minus the origin, I can find an affine variety that's homotopy equivalent to it in motivic homotopy theory. Now, that actually, you can just modify this a little bit and do this for any quasi-projective variety. So to any quasi-projective variety, you can find an affine variety that's homotopy equivalent. And this is called Joannolu's device. And if the variety you started with is smooth, so is Joannolu's device. Okay, so let me see. I gave another example. I wanted to give you the example for projective space because that's going to play an important role later on. And the simplest way to do it is to just make that ring I wrote down into a graded ring by giving x degree 1 and y degree negative 1 and looking at the degree 0 part. In geometric terms, what the Zhawanolu device for projective space is it's the space of rank 1 projective operators on n plus 1 space. So the line is the image of the projection operator. That's an affine variety, and it's a homotopy equivalent to projective space. Anyway, this will play a role later on, so I wanted at some point to have explicitly mentioned the ring. So that lets us build this little diagram. We have motivic vector bundles on a smooth variety. Because the Zhawanolu device is homotopy equivalent, that's the same as motivic vector bundles on the Zhawanolu device. And that, by the theorem of Morel and Asok, Oiwa, and Wendt, is the same as algebraic vector bundles on the Zhawanolu device. So the relationship between motivic vector bundles and algebraic vector bundles on non-affine things is also a problem purely in algebraic geometry. It's the problem of whether or not a vector bundle up on the Zhawanolu device is pulled back from a vector bundle on X. And that also seems to be a very hard problem. I don't know of any counterexamples to that, but again, if that was true in general, you would know counterexamples to famous conjectures. But nevertheless, so this theory of motivic vector bundles, it means something. It does sit in between topological and algebraic vector bundles, but and the relationship, so on affine things, those are algebraic vector bundles, and on projective things, the relationship between them has to do with the difference between vector bundles on X and on the Zhawanolu device. Okay, so that's a long kind of wind up in setting the stage, and now I want to actually talk about using the methods of homotopy theory to investigate these motivic vector bundles. And that gets formulated in any abstract homotopy theory in terms of obstruction theory. So in spaces, we can study the maps from X to Y in terms of, well, this is Steenrod's obstruction theory, in terms of the cohomology of X with coefficients in the homotopy groups of Y. And one of the lessons that comes out of abstract homotopy theory is that this always holds. In every abstract homotopy theory, it has its own internal notion of homotopy groups and its own internal notion of cohomology, and there's always a relationship like these. Sometimes these homotopy groups and cohomology groups are invariants people studied but weren't aware were in this relationship, and sometimes they're completely new invariants. So let me just go through and tell you what this looks like in the three categories we've been looking at. So in algebraic homotopy theory, the homotopy groups of this classifying space are just 0 when I is not 0, and the group you started with when I is equal to 1. And the obstruction theory doesn't do anything. It just recovers the isomorphism of rank K vector bundles or principal G bundles as H1. But as I told you, that category is very formal. You don't kind of penetrate into the structure of the objects in any significant way. In motivic homotopy theory, it's very different. The homotopy groups are now sheaves of a very special kind, but I don't want to get into that. So pi 0 is trivial. The fundamental group is the sheaf GL1, and the second one is what's called Milnor-Witt K theory, and it's related to the K theory introduced by Milnor in his paper on algebraic K theory and quadratic forms. So that, the appearance of this Milnor-Witt K theory in the homotopy groups of the classifying space for rank 2 vector bundles brings that invariant, it lends it some significance in the classification of vector bundles. So what you're supposed to come away from this with is this idea that in motivic homotopy theory, the obstruction theory and the cohomology, they really do kind of penetrate and decompose the structure of the objects you're looking at in ways that are unfamiliar if you're looking at it from the point of view of classical algebraic geometry. So this already has many applications. Morel and Asok and Fasel investigated problems like finding free summands of projective modules over regular rings, and they had a lot of success in low dimensions. So there's a paper, right, so Jean and Aravind and I got looking at this and thinking about this work of Griffiths from the 70s. And in the 70s, so there was this, I don't want to call it a belief. So Griffiths was working on these in order to solve the Hodge conjecture. So if you had a vector bundle, and the whole point was to realize cohomology classes as Chern classes of algebraic vector bundles. So there was a philosophy that if the Chern classes were algebraic, the vector bundle was. But I don't know how seriously anybody took that. It's a philosophy that's in the papers, but for the problems of interest in that era, assuming the Chern classes were algebraic was giving away the game anyway. Nevertheless, we got interested in answering that question. Suppose you have a complex affine variety and a complex vector bundle whose Chern classes are algebraic. Then is the vector bundle algebraic? And the answer is no. So you can use Steenrod operations, and though that kind of Steenrod operations relating things like Milnor-Witt K groups and stuff like that, you can use that apparatus to show that there's a smooth hypersurface of bi degree 3, 4 with a rank 2 topological vector bundle on the complement, so that complement's an affine variety that has algebraic Chern classes, but it's not algebraizable. So this was just something, I think this is just something that illustrates kind of the power of these techniques. And one thing I find really interesting, but we haven't had a chance to even start to explore it, is to try to understand the relationship. So this involves Steenrod operations in relating these kind of strange cohomology groups. In principle, there must be Griffiths obstruction to algebraizing this vector bundle, which is something expressed in terms of value distribution theory. And there must be a relationship between these Steenrod operations in Milnor K theory and value distribution theory. But I have no idea what that relationship is. But this is a project we're very interested in approaching. So this, I think, is one place where you really do see a problem, like Maury was talking about, where I looked at from one point of view, we can study Steenrod operations and solve it, but it's also something that has an expression in terms of complex analysis, and trying to find the relationship between those is really fascinating. Okay, so that's one theorem using these abstract methods that applies to vector bundles on affine varieties. What about vector bundles on projective space? So this is a very famous problem to classify rank 2 bundles on projective n space. This problem has a long history, and it gets expressed in a famous conjecture of Hartshorne that says if n is greater than 5, every rank 2 bundle is a sum of line bundles. So this has an interpretation in terms of codimension 2 subvarieties of projective n space. And so as I say, this problem has a long history. There was something I'll call the Grauer-Schneider problem. This was, it was a theorem for a little while, and then an error was found in the proof. But what the assertion was that if n is greater than 3, every unstable rank 2 vector bundle is a sum of line bundles. So unstable is in the sense of Mumford, but if the Chern classes are 0, then the bundle's unstable. So in particular, if you had a non-trivial, in particular, Hartshorne's conjecture implies that if you construct a vector bundle of rank 2 on Pn for n greater than 5, with no Chern classes, it better be trivial. So the Grauer-Schneider problem is a special case of Hartshorne's conjecture. Well, let me just go on. So in the 70s, there was when the Grauer-Schneider problem was a theorem, there was a little bit of a mission to search for topological vector bundles with vanishing Chern classes. And as you can tell from the title of that paper, Elmer Rees produced some bundles, and he produced some infinitely many vector bundles on Pn with no Chern classes. And so if you knew that the Grauer-Schneider problem was true, this would imply these vectors have no algebraic structure. We don't know the Grauer-Schneider problem, and to this day, there's no known example of a topological vector bundle on projective space that doesn't have an algebraic structure. So I want to talk a little bit about these Rees bundles. And in fact, it was Elmer Rees that got me interested in this problem in the first place. So here's how the Rees, this is a good illustration of how obstruction theory kind of takes apart a problem like this. So the rank 2 bundles on projective n space is homotopy classes of maps into the classifying space of the group of 2x2 unitary or 2x2 invertible matrices. And if I wrote down the obstruction theory in topology, that involves the cohomology of projective space with coefficients in the homotopy groups of this classifying space. And projective space has only even dimensional cohomology, so I've just written those as even. And so I'm interested in knowing about the even homotopy groups of this classifying space of U2. And those work out to be isomorphic to the odd homotopy groups of the 3-sphere. So if I understood something about the odd homotopy groups of the 3-sphere, I might be able to say something about topological vector bundles on projective space. Well, one does know something about the odd homotopy groups of the 3-sphere. In the first place you have one, you have an element of order p in pi 4p minus 3. So what Rees did was he studied vector bundles associated to that element. And in particular, he studied this one on complex projective space of dimension 2p minus 1 that's gotten by that composite of maps that I've drawn there. And these bundles, because the classifying map factors through the quotient of that projective space by the one just lower, they don't have any Chern classes. So he proved that these were non-trivial, they have no Chern classes, and so by the standard philosophy, they're predicted not to have an algebraic structure. All right, well, at the beginning, when I got done setting up all this abstract homotopy theory, I introduced these 3 categories, and it's believed that this bundle doesn't have an algebraic structure. Does it have a motivic structure? Maybe we could use the Steenrod operations in Milnor K groups and things like that in order to show that it didn't have a motivic structure, and then that would at least give an example of something that doesn't have an algebraic structure. Well, it turns out it does have a motivic structure, and I want to say a little bit about that in a minute. And you can translate that into into a problem, into an assertion in algebra. So it says there's a module over that ring, J0, the degree 0 part of that ring I wrote down. There's a rank 2 module with the property that when you add a free module, a rank 2 projective module, so when you add a free module to it, it becomes free, but it's not free. And you know it's not free because when you realize it in topology, it corresponds to this interesting non-trivial vector bundle. So this is a rank 2 module I have no idea how to construct, how to write down using algebra. And I'm going to take you through a little bit of the construction of it to show you kind of what it is that motivic homotopy theory can do that you can't do, or we don't know how to do, just in terms of rings. But I just want to emphasize, there's a ring, it's very easy to write down. We have a rank 2, we have an interesting rank 2 projective module that we have no idea how to write down. So this element in pi 4, these Reese bundles come from this element in pi 4p minus 3 of the 3 sphere. And the key step you need a good geometric or linear algebra construction of that map, and the key step is the existence is this diagram. Now this map from GLNC to the 2n minus 1 sphere is just taking, say, the first standard basis vector, or just taking the first column, say, of a matrix, an n by n matrix, and looking at the unit and dividing it by its norm. Okay, so that's the quotient. If I had written un, that's the quotient of un by un minus 1. So that doesn't have a section, but if you compose it with the map of degree n minus 1 factorial, it does have a section. Now this is a well-known fact from K-theory. This is used to construct the generator of the K-theory of S2n, and that n minus 1 factorial was a number produced by Bott, and it has to do with the top Chern class of that bundle. Okay, anyway, using that, you build a map from the 2p sphere to the 3 sphere, and you compose that map with its 2p minus 3-fold suspension to get this element in pi 4p minus 3 of S3. So in order to do this in motivic homotopy theory, we would need to do all of these steps. Now I was talking about spheres, so I better tell you what the spheres are in motivic homotopy theory. And there's, so they're like topological spheres. They have a dimension, but they also have a Hodge weight. There's 2 indices. So I've given you some examples here. The S11 is the affine line minus the origin. You're supposed to picture the complex numbers minus the origin, so that's a circle. You could also take the affine line, think of it over the reals, and just glue 0 and 1 together. That gives you another sphere with Hodge weight 0. And using some standard methods, you can build other spheres out of those. So affine n space minus the origin is 2n minus 1 dimensional and has Hodge weight n. And projective n space mod that's supposed to be a pn minus 1, has a dimension 2n and Hodge weight n. I see that time is kind of getting away from me, so sure, there's homotopy groups as well, and you can realize these to ordinary groups in topology. Anyway, the key thing is to produce this key diagram, right? Given we're supposed to produce a map from that odd sphere to itself of degree n minus 1 factorial that factors through GLN. Now, I wrote it this way, and I used the Joannolu device for affine n space minus the origin, because general principles tell you this diagram, if it exists in motivic homotopy theory, actually has to exist in algebra. And it has an algebraic interpretation. So this says, given 2 vectors, x and y, whose dot product is 1, that there's an n by n matrix. Well, not with the first vector. The naive thing would be there's an n by n matrix whose top row is that vector. That would be the same thing as having a section of that map. We don't expect that. In fact, we know there can't be one, but we might hope for one of degree n minus 1 factorial, and that's saying, well, I don't put the original vector in the top row, but I raise the entries to some powers whose product is divisible by n minus 1 factorial. And it's an amazing, I don't know where this came from, but it's an amazing theorem, a whole theory of Suslin. This is Suslin's n factorial theorem, and it's part of his theory of unimodular rows that says exactly that you can do that. Given 2 vectors whose dot product is 1 and some exponents whose product is divisible by n minus 1 factorial, you can find a unimodular n-by-n matrix whose top row is that. So Susslin's theorem, his theory of unimodular rows, gives you this key step, and everything else is formal. I want to put it up because there's this extra piece of information in motivic homotopy theory, which is the Hodge weight. When all this is done, you can imitate the exact same construction, and you produce this element in pi 4p minus 3 of S3, but it has Hodge weight 2p. But if you think about what we needed to make a vector bundle, so that was eventually supposed to be a map from a projective space mod, a lower one, we were supposed to get a map from S4p minus 3 to S3 where the Hodge weight was 2p minus 1. So the Hodge weight is wrong. And this seemed like an exciting thing at first because it looked, what do you have in motivic homotopy theory that you don't have in ordinary homotopy theory is the Hodge structure. And it really felt like this was going to be a way of using that to obstruct the existence of this bundle. But in motivic homotopy theory, there's an operation on torsion elements that lowers the Hodge weight by 1, and it realizes under topological realization to the identity. And you can apply that and lift the Riesz bundles to motivic vector bundles. So once you realize that you can kind of move the Hodge weight around, it gives you this sense that maybe motivic vector bundles over things like projective space aren't so different from topological vector bundles. And I'll come to that, and I'm going to finish on that in just a second. But let me just come back here. We've shown that these Riesz bundles lift to motivic bundles, and now we have explicit vector bundles over the Joanolu device for projective space. Either they're examples of things that don't descend, those would be new examples, or they do descend and they're counterexamples to the Hartshorne conjecture. So these are fascinating objects, and I think they're very concrete, and I think, well, as I just said, one of two things is true about them, and they're both, either one would be interesting. Okay, I want to wrap this up in just a minute. So I'm going to be a little bit brief about this last point. But as I said, being able to move the Hodge weight around, it makes it hard to think of things that are really going to stand between ordinary homotopy theory of things like projective spaces and motivic homotopy theory. And in ordinary homotopy theory, there's a really fantastic way of taking things apart into pieces involving something called complex cobordism. And I just want to, and there's something that makes it very powerful, and I think this is one of the best kept secrets of algebraic topology. So in algebraic topology, there's this amazing class of spaces that have no odd homotopy groups and no odd cells. So something like infinite dimensional complex projective space, or the classifying space for the unitary group, or the classifying space for K theory. Another example that's non-trivial is the classifying space for bundles whose second Chern class is 0. That has only even homotopy groups and only even dimensional cells. So these spaces are called even, and Steve Wilson in his thesis showed that the classifying space of complex cobordism is even. Now I don't have time to go into why that's such a powerful thing, but it allows you to build to resolve spaces in unexpected ways in terms of Eilenberg-MacLane spaces. So Asok and Jean Fasel and I, we just explored the analog of this in motivic homotopy theory. So there's an obvious analog of the definition of even motivic space, and we've been exploring something we call the Wilson space hypothesis, which is that the classifying space of algebraic cobordism is even. So if you knew this, let me just say, This allows you to make some really unexpected resolutions, and I put this in quotes because we haven't really worked out all the details, but things look pretty good. It implies that if the Wilson space hypothesis holds, it implies that this little thing about moving the Hodge weight around was part of something much stronger, and it says that there's no difference between topological and motivic vector bundles on projective space, or more generally anything with an algebraic cell decomposition. So this is a very interesting hypothesis, and oops, I wanted to go back and just ruminate on that for a second. Well, maybe I won't since time is short. I'll just, let me just summarize here. So I started with this question about which complex vector bundles on complex algebraic varieties have algebraic structures. And this doesn't seem to want to advance. And so here's the diagram that kind of summarizes what I've said. The Wilson space hypothesis would tell you you can, for when they have algebraic cell decompositions, you can lift every topological vector bundle to a motivic bundle. Then this theorem of Morel and Asok, Oiwa, and Wendt would tell you that's the same as vector bundles over the Zhuang-Lu device. So the Wilson space hypothesis, it locates the question of when a topological vector bundle has an algebraic structure on these kind of varieties, on projective space, entirely in algebraic geometry. And it's the question of descending vector bundles from the Zhuang-Lu device to the variety. Okay, anyway, I'll stop there. I look like I've gone over time, so thank you.
¿Preguntas o comentarios?
Okay, what method do you expect to the proof of the Wilson's hypothesis?
Well, I think we need to build a model for that space. The method in homotopy theory it's an elaborate calculation that just kind of appears to produce the answer by accident. And what we're currently trying to do is take some constructions that give varieties with algebraic cell decompositions, like quiver varieties and things like that, and trying to use those to make a model for the classifying space for complex cobordism. So that result seems to be true in many, many, many categories. Mike Hill and I have shown it's true in certain kinds of equivariant homotopy theory, and but really, we're looking for a reason that it's true, and even in ordinary homotopy theory, writing that as some kind of co-limit of varieties with cell decomposition is that's what we're trying to do. Yeah.
Thank you. So maybe I didn't catch it, but so what you're claiming is that the lifting of these Rees bundles, and you lift them to that JP and then push them down to Pn, that will give you an example of a decomposable vector bundle for n.
Yeah, I'd give you a non-trivial vector bundle on Pn with no Chern classes. So if it was decomposable, it'd have to be trivial.
Right.
But yeah, that could be just as hard as the original problem. But these bundles over the J are already new.
Okay. So any.
Yeah. No. Good.
So you mentioned that when you have motivic Beck mod homotopy being being the same as algebraic Beck, this would give counterexamples to many conjectures. What would be the most typical conjecture that it would give a counterexample?
Well, it would prove that every vector bundle on the Zhuang-Lu device comes from one on the on the projective space.
So it would give this.
It would give that, yeah. It would give the surjectivity.
And Mettler-Harshorn's conjecture would be false then.
Yeah, yeah.
Okay.
But I don't have an opinion about Harshorn's conjecture. I just, but yeah, that naive guess would imply that. That's right.
More questions? Okay, then let us thank the speaker again.